cuprate superconductors. So I'll just give you a little bit of an introduction, at least in the way I see, for whatever I think is important for you to follow the rest of the talk, and then I'll sort of get into, be a little bit of a progress report. We've had a little bit of progress in the past, and I would like to share that in that recent past. Let's see, how do I do? Yes. So, all right, so general slide. I mean, quantum materials is really you would like to have some form of microscopic control that allows you to engineer rationally the Hamiltonian. There's a lot of interesting things. This is the flavor du jour for the past few years. We've been betting on this periodic driving. So it's some form of Floquet engineering, except that it relies on coupling to normal modes, collective modes of the solid, because we believe that this is a much better way to do Floquet, because you have a transducer that allows you to sort of put in the electromagnetic radiation. But if Floquet is what you like, think about it in terms of so a lot of what we do is using light that couples to infrared active photon modes. So these would be long wavelength, the zone center, k equals 0. Photon modes that have a dipole, and they break inversion, so they're odd in symmetry, and you can drive them with light to large amplitudes, and you would like, if the light field is large enough, you will be able to drive large displacements. There's a lot of conceptual analogy with the physics of driven lattices. So this is actually being, so imagine a crystal and you sort of shake it. There's really, in synthetic quantum systems, people have really sort of done a lot of stuff. They've seen, either they look at phenomena that you would like to understand at equilibrium, or they discover new physics in the driven state. So imagine the shaking of phonons as something related to this shaking of the optical lattices. So this is a little bit of a laundry list of things that you can do. You can drive the structure from structure A to structure B, and sort of reveal hidden phases that don't happen at equilibrium, but nevertheless are in the texture, in the free energy space can be found. You can switch things like ferroelectricity that relies on basically inverting dipoles, and this is actually interesting also for potential applications. You can, this is not great, you can couple to other degrees of freedom. Magnetism, you can do things such as induce ferromagnetism, ferrimagnetism. There's also a lot of work that we did by driving phonons, sort of artificial gauge fields, so making phonons rotate. So this is again stolen from the cold gas protocols. So James McIver is here. So there's been work in trying to induce topology by using circular polarized light.
Even if you're nearby, it doesn't work?
No. Well, nearby. Oh, I see. Let's see.
It should work actually. You need to point to the
I will point.
USB.
Okay. Right. Okay. Thanks. So this is on all these things that I told you, a very, very interesting, at least in the way I see things, sort of set of problems is to try to enhance or reduce superconductivity in an interesting way. So let's think about superconductivity as a mechanism in which you create bosonic paths, which then become locked in phase. Either, whether you're weak coupling or strong coupling, these things will happen either simultaneously or on different scales. But these are the two problems. And by using this coherent electromagnetic radiation, you would like either to enhance or reduce these pairing fields, or to enhance phase. If you think about the problem as a Bose-Einstein condensation problem, you can add rigidity to the phase, like some form of dynamical modulation. So this is very intuitive, but this is what we're very interested in trying to do. So this is an old problem. People have used microwave radiation to enhance superconductivity in the past. This is the celebrated BCS experiments, first seen by Wyatt and a number of other groups, who showed that if you irradiate a superconductor with radiation at frequencies below the 2 delta gap, so you don't break the Cooper paths, but you heat up the quasiparticles, you can enhance superconductivity. And this is done according to the Rashberg's theory, because basically by heating up the quasi-particles without destroying the Hooker pairs, you reduce the density of quasi-particles at the 2 delta energy, and the system likes not to have too many quasi-particles at 2 delta. So you have higher TC, higher critical currents. But this is a small effect, and you know, people have only, you know, somehow sources did not allow comprehensive exploration of many frequency scales. So when people did these experiments, you could either go to microwaves or go to EV scales, but nothing in between. There's also, so we've done a number of things. Again, laundry list. We've worked a lot on organics. I won't tell you about organics today. But for example, in these doped fullerenes, this is something that was discovered by Matteo Mitrano, who's now local here. And then there's been a number of studies after we showed that if you drive some vibrations in fullerenes, or if you drive some molecular modes in these Chuck's transfer salts, you can enhance superconductivity. This would be, each one of those would be a separate one. Then there's been work in the cuprates. And this again splits into 2 sets of experiments. One which was discovered by Daniele Fausti, who was also in the audience. One in which you can use light to destroy a competing order that stifles superconductivity, thereby resurrecting an in-field superconductivity by destroying this competing order. Or a second mysterious process, which we have been working on, but also spectacular, in which you take YBCO, which at the beginning we thought we could basically, we could do the same thing that we did to these striped cuprates to YBCO in this specific region and enhance superconductivity, but it turns out to be a much bigger, sort of a more surprising set of effects. So just this work in the stripes has been recently confirmed by at least 2 groups. So this is the San Diego group, and this is the Shimano Tokyo group that showed that confirmed and interpreted more or less in the same way. So this is today's talk, YBCO. Okay, so YBCO. So the again summary of what we did for the past 10 years. What you do is you're going to try to drive YBCO, and then you need something that tells you that the material is either superconducting or not superconducting. But you cannot look at zero frequency properties because the effect is transient. So the zero frequency properties are those of a metal, meaning if you wait long enough, the material is not superconducting. So you have to look at the AC response. One way to look at it is to look at the terahertz frequency optical properties measured with the polarization perpendicular to the planes. These are the superconducting planes of YBCO, which are coupled by tunneling. And if you measure in equilibrium this effect and you cool below TC, what you find is loss of spectral weight in the resistive real part of the conductivity and the formation of a delta function, a pole at zero frequency sigma 1, that is reflected in the divergent sigma 2 conductivity. So the fact that this thing diverges like 1 over omega tells you that there's a pole here at zero frequency. Now, what we're going to do is an experiment in which this is YBCO, these are the superconducting planes. And what we want to do for our flow K transducer is to modulate the position of this particular oxygen atom. So imagine the 2p orbitals of an oxygen atom that go in and out from the superconducting planes and hybridize or not hybridize depending on the distance. And so they allow you to just put your flow K drive into the Hamiltonian effectively. And you know at equilibrium that the position of this apical oxygen in equilibrium correlates with superconductivity. In other words, you want the apical oxygen to be as far away as you can from the planes, so that this is a really very nice 3D x squared minus y squared orbital, and you have no 2p thing bothering you. But we're going to do the shaking, and this is going to be a periodic effect. So if you do this, what you find is that the photoinduced state has a dissipative response. In other states, in other systems, we find gapping. In the specific case of cuprates, which are very insulating along the c-axis, you have hot quasi-particles in the real part of the conductivity, but you get this very nice 1/omega response, which has a couple of features. Feature number one is that if you take these optical properties and you fit them with a Drude model, you can define a figure of merit, which would be the extrapolated, let's say, conductivity of the system by extrapolating the limit of frequency that goes to 0. And so you can use this as a figure of merit. So this would be the inverse. So if this were a superconductor, this number would be 0, meaning rho would be 0. And so if you do this, you find that whilst the material is being driven, you get that the resistivity extracted with this procedure goes down by many orders of magnitude. And if you make the pulses longer, this is recent work done by Amit Ribak. We've been pumping with pulses all the way to 4 picoseconds. This extrapolated zero frequency resistivity, or very low frequency resistivity, stays 0 as long as you drive it, and then stops being 0 when you're done driving it. So again, in the spirit of low-K engineering, and you find the zero frequency state, zero resistivity state. And also, you can also take, this is the data, the 1/omega response in the transient system with the modulation of the apical oxygens. And this is the 1/omega response of the same material at zero frequency, at zero temperature. And so the 1/omega-ness of sigma 2 tells you what the transient superfluid density of the system is, because it's proportional to the spectral weight of the delta function in sigma 1. And so what you find is that if you pump it with a pulse that is long enough, so you pump it hard enough, you find that you recover exactly the superfluid density that you have in the same material when you cool it to 0 temperature. So all this cannot really be a coincidence. There's something, this transient state really looks like the zero temperature thermal state, at least in terms of the optical properties. Again, so this is old story. Lots of people have different opinions about this. I can tell you mine if you're interested, but right. So the other, I'm so sorry. The other interesting thing that makes this discussion very sort of emotional at some level is that when you look at how far you can drive this state, you can find it in excess of room temperature. And depending on the doping, it kind of overlaps with this mysterious pseudo-gap phase, which is found in underdoped cuprates, which is something, it's a gap state that has the same dx squared minus y squared. Symmetry has it's a weak diamagnet, has a lot of features of the superconducting state, but not really well formed. And you can do this all the way, for each doping, you can do it all the way to this pseudo-gap temperature. Again, underscoring a sort of a connection with the equilibrium phase that is probably suggested. Right, okay, so I'm going to tell you 2 things today. Point number 1, this is all very nice and it's very suggestive, but it's not a conclusive explanation, and as referees don't frequently mention, because what you want to see is that this material is a diamagnet and has the Meissner effect. This is not a small diamagnet. This has to be a colossal diamagnetic response. It means that basically it's chi needs to be either somewhere between in the in-field cooling. It can be anywhere between a few percent to 100%, which is many orders of magnitude higher than anything else. So we've been sort of working on trying to validate or just check whether this state expels a magnetic field, because at a priori we can't tell, because this is not a superconductor-like state away from equilibrium. So this is the work of 2 PhD students of mine, Giovanni De Vecchi and Sebastian Favo, who worked for the past 5 years to try to do, this is going to be split, this is split between 2 people. So there's going to be 3 curves that I show you, but it's really been a bit of a tour de force. So, and this has been work also led by Michele Buzzi, who's a staff scientist in my department, and Gregor Iozzo, who actually has an interesting path. He first worked as a cold gas experimentalist, then came to work with me, and now he joined the EPFL faculty, and he's somewhere, I don't know exactly what he's going to do, but he's sort of certainly is an extremely talented experimentalist who has helped us a lot. Okay, so this is what we're trying to do. remember, what you need to do is the in-field Meissner effect. If you remember from the textbooks, you can't just cool the material, turn on the magnetic field. You need to keep the magnetic field up and cool it down. And that's what you, so what we're going to do is a proxy for that. We're going to have a DC magnetic field, and we're going to excite in-field. Because we don't want to see magnetic field exclusion. We want to see magnetic field expulsion, which is a property of a superconductor as opposed to that of a perfect metal. And so we're going to pump this, and the field lines, as this material becomes a good diamagnet, are going to be strained, so to speak. And so transiently, I should find a state in which the field lines are basically zero here, or close to zero, and they get more compressed. So there's a demagnetization factor. The magnetic field should go up here and go down there. And so the problem of measuring this is that you need to find ways to measure the magnetic field immediately outside the material. You cannot use a squid because a squid doesn't work at room temperature. So you need to kind of get creative about this. And also squid wouldn't be fast enough to measure this. So the way we did this is to take YBCO, we slap a piece of a magneto-optic material, say either a garnet or anything that has a finite Faraday effect, we will be able to probe the magnetic field inside this external material outside YBCO. So if we apply a field and we look at the polarization rotation of the reflected light pulse, we should be able to diagnose the density of the field lines immediately outside the sample. And potentially this can be done at very fast speeds because you can make this pulse very short. So that's basically the plan. So there's a couple of things that we need to do. First, we need to calibrate, is this real? And can I measure the Meissner effect? So you can do this in equilibrium. You take your material. So I'm going to plot here B measured outside divided by the applied field. So I'm now going to start above TC. This material is a vegetable, is a weak diamagnet. So the fields should be the same as the applied field, which means that this number should be 1 everywhere. So I can now scan my polarization rotation, and I can see that at room temperature, in equilibrium, YBCO has the right, and is a weak, doesn't really have much magnetic activity. So now I cool below TC, and there's not too much animation here. So I scan this, and here I find that the magnetic field gets more intense immediately outside and becomes 0 inside. So calibration number 1 works. You can use this method to measure the Meissner effect in equilibrium. Now the first thing, then this calibration number 2 needs to be, let's do something that everybody believes before we get into our whole conversation. So we take a material, we use what we call a smash beam. So we use a UV light pulse in a superconductor below TC. We destroy superconductivity. So this is work, this is data taken by Rick Avery when he was in Los Alamos in the early 2000s. You can see below TC, the equilibrium state is this 1 over omega response. You smash it, you look at the turrets, in that case was, I think, transmission, and you see that the 1 over omega disappears. So we should be able to do this by doing this Meissner effect measurement. Again, so this is basically, this calibration is basically Giovanni's PhD thesis. It's really, turns out for various reasons to be a difficult thing to do. And so what he did, he took YBCO thin films. What you don't want to do is to pump the detector, because otherwise you're doing pump probe in this. So what Giovanni started doing was to pump from the back a thin film and probe superconductivity in the front with various layers grown here to sort of separate the pump and the measurement. And now we start below TC, remember. I have high field in the outside and 0 field on the inside. So now I pump in the I pump here and probe in the center, and you see that the field goes from being completely screened to being sort of completely let through. And now if I go on the outside, on the edge, where the field is higher than the applied field, what we see is that it goes from a number that is larger than the applied field to the applied field. So calibration number 2 also works. You can take a material with a nice Meissner effect, and you can show that this Meissner effect goes away. And you can kind of, I mean, there's lots of things that you could try to understand, time scales and everything, but at first sight, this looks we should be able to use fabrication methods like focus ion beam with our colleagues in Hamburg, but at the minute we can only use bricks. So we can only pump in the center and look on the outside. So what we do is we pump the apical oxygens here. Then what we have is an aluminum oxide mask that makes it such that the pump doesn't touch this part of the material. And then we have gallium phosphide that for various reasons is a good detector of the polarization of rotation. So what we want to see is that if we pump here, we can see an enhancement in magnetic field out here. So, great, it works. So this is now the enhancement in magnetic field outside of the material at 100 Kelvin, so about 2 times above TC, and at room temperature. And this is the, if you assume that this is an adiabatic process, which it isn't, and you take each one of these points as being a quasi-static point, you can solve the magnetostatics and extract which chi this corresponds to. And you can see that at room temperature, you get about minus 10% chi. Just to renormalize you, graphite has the largest diamagnetism of any material that is not superconducting, and it's somewhere of order, 5, 10 to the minus 4. YBCO field, this YBCO field cooled has about 1% in equilibrium, and whereas this is where we find the light-induced. Optimally doped YBCO has a field cooled chi of about minus 10%. So this is, however you slice this is an enormous photo-induced diamagnetic phenomenon. You can also do all sorts of checks. You measure polarizations, and you show that because this is a Meissner effect, it cannot have lobes. You don't want to be measuring Pockels effects or various nonlinear optical phenomena. This needs to be isotropic. There's no other, anyway, we can discuss the details. You basically doing the experiments by chopping multiple things. You chop the magnetic field, you chop various pumps, there's a number, and so you can identify the right response. Right, so one more check. Now we're trying to extract really what the photo-induced diamagnetism looks like, and you immediately recognize that this is an electrodynamic problem because you change the magnetic field here, you have a dB dt here, which in the spirit of the Huygens principle will radiate. And so you'll have a magnetic field wave that propagates. So Sebastian is a persistent guy, and he's sort of measured at various points in space. This is, this is the quality of the data at near room temperature, but you can see that the group of this magnetic field pulse that propagates along YBCO moves at the group velocity. So it seems that things, do what you're supposed to do. Right, and the temperature dependence is exactly the one that you observe in the optical response, and it correlates with the pseudogap scale. So we've only checked one doping at the moment. Of course, in the future we'll try to do more comprehensive things, but the obvious things seem to do what they're supposed to do. So how much time do I have? Because I want to tell you. Fantastic. Okay, so basically, we can discuss the details. Light-induced state, you generate a transient superfluid density that is the same as the zero temperature superfluid density in the same material, and you get an expulsion of a magnetic field that is too large to be anything else, and is larger than the diamagnetism that you find in the same material in field cooled. So now that there's a whole set of other things, we've been trying to understand, what's going on, basically. How is it? I haven't told you anything about the microscopics of this problem. This has really been one of those things that you discover, and then you just try to fill in we didn't really have in the other experiments, we would sort of melt the stripes. But in this case, we really have no idea what's going on. So we started early on positing that this excitation of the phonons must be creating a transient crystal structure that is different from the equilibrium crystal structure, that maybe is more conducive to superconductivity. So we did, this is 10 years ago, we did experiments using the LCLS free electron laser. We were collaborating with Andrea Cavalleri, who was our theory friend at the time. So we measured a bunch of peaks and we reconstructed, based on the theory of nonlinear phonons, elementary theory of nonlinear phonons, we reconstructed a transient crystal structure of the state, and we sort of discussed what this, whether this may or may not be the source, whether this new crystal structure may or may not be the source of a higher temperature superconductor, which then would be very interesting because you could then convince a chemist to try to sort of grow a structure like this, and then you'd be making a room temperature superconductor. So this was great because Roman Minkowski graduated and he did well, but then I don't think this is the reason why we've been pursuing this idea of a transient quasi-static crystal structure for a while, but I don't think that this is the reason. So I'm going to tell you how much progress we've made with our chairman. So this is the problem. If you strip it down to its simplest, in its simplest form, you're driving this apical oxygen and you're trying to enhance the superconducting tunneling between the planes. Because this is a bilayer structure, you really have two superconducting tunneling modes. These are coupled by the Josephson effect. Imagine this is a molecule. You have two plasma modes. One, you have supercurrents that are in phase between the bilayers and within the bilayer. And then there's a higher frequency one where the tunnel, you have tunneling in antiphase when you look at the currents within the planes and between the planes. So these are this is a three-mode problem where you take this phonon, you smash this 2p orbital onto the planes at high frequency, and you try to understand what these guys are doing, below TC and above TC. So this is a very beautiful theory that Marius Michael, who was a student with Eugene at Harvard, put together. That's the lowest order sort of theory that you can put together. What they said is, if you write the energy of this problem with these three modes, there's going to be, at lowest order, there's going to be a mixing, trilinear mixing term. These are three odd modes, which so we will be finite only at finite momentum. But you should have, if you write down the energy of the system when this phonon is being driven Q, you should have this trilinear coupling between Q and these two Josephson tunneling modes. Now, those of you that build lasers will immediately recognize the equations of an optical parametric amplifier in this. So if you write the equations of motion for the driven phonon, which is this is now dispersion in Q, this is my phonon that I'm driving. These are the two tunneling modes, these are plasmons that disperse like so. And what you will find is that basically, because of the trilinear mixing term that I told you about, there is a resonance condition where if the frequency of the driven mode is equal to the sum of the frequencies of the two plasma modes, you basically will have the equations of a parametric amplifier. This is a very pretty prediction because it posits that you will be able to take superconducting fluctuations that are very weak, and by driving the phonon, you're going to amplify them in the same way as you amplify a laser mode when you build an optical parametric amplifier and create a time crystal. This is going to be the ultimate time crystal. There's a parametric process where you grow a mode in some interesting place, not at omega divided by 2, which does something useful. So this is now, was my student Alex von Hoeken, who's now a postdoc with NU, and he set up a very interesting set of experiments where he would pump my YBCO and he would use a probe pulse and he looked at the second harmonic generated at the surface. All you need to know is that if you measure second harmonic as a function of pump probe time delay, you'll be able to measure modes that are odd in symmetry, that break a mirror as they oscillate, and they will modulate chi2 at the surface. So this was actually a long story. So this is Alex's curves. They look like this. You can take all these oscillations, you can Fourier transform them and compare the response of these oscillations to the excitation of the phonon, which is a different frequency, to Marius and Eugene's theory. And so that theory makes 4 predictions. Prediction number 1 is that driving a phonon at 17 terahertz should generate 2 peaks. These are Fourier transforms, experimental Fourier transforms of the oscillations that Alex took. Should generate 2 peaks, one around here, around 15 terahertz, and one around 2 terahertz. So check. This is, you really see a peak, and then you need a little bit loving eyes here, but you can convince yourself that there's 2 peaks that the sum of which add up to the pump phonon. The second prediction of their theory is that, and this is very beautiful, is that if you plot the amplitude, sorry, just saying clearly, the amplitude of this plasmon oscillation as a function of the amplitude of this, which is the phonon, which you're measuring directly by measuring the second harmonic as it oscillates in time, you should have an exponential growth of this as a function of that. And what Alex found, look at this. This is sort of the experiment. If you do everything right with the error bars, it's very pretty demonstration that you're amplifying this Josephson currents exponentially as a function of the phonon. 10 minutes, yeah. So we're getting there. Yes, Mohammed.
Are you seeding it or it's a spontaneous
I'm
generation?
going to get there. This is good. No. So the pump is carry-envelope phase stable, but the amplified fluctuations start from a thermal noise. So that's exactly what we're talking. Okay, anyway, hold your horses. Just you haven't thought about that yet. Imagine. Just erase that from your mind. I'll get to it. So now, if you erase this thing that you said, astutely, you could say, okay, very nice there. The 3-wave model works very well. You amplify. The third thing that they predict is that this effect should be zero at zero momentum, this amplification, and should peak at 2 momenta that the system chooses to conserve energy and momentum. And so Alex's data, you can look at a bunch of things, and you look at the amplified mode, and it's actually kind of zero at zero momentum. So what he does is he looks at the second harmonic, not in specular reflection, but as a function of angle from specular. And so what he finds is that this then peaks exactly at the wave vector that the Marius theory says it should. And finally, you can look at the flowers as a function of time. This is a little bit of a nonlinear optics trick, but you can convince yourself that this mode is very special. This is not a phonon flower. The B1U phonons that break a mirror twice a cycle, they look like beans, 2 beans. Whereas this is some high order, low symmetry mode that is related to this finite frequency. Great. Paper was submitted, was rejected in Science, published in PRX, everybody's happy, and so we thought we're making some real progress. Now, the other thing that you can see, prediction number 5, is that the temperature at which this effect happens should happen in the pseudogap phase, because you need pre-existing fluctuations of the Cooper pairs to start this. And so this should be a function of doping and should go away on the pseudogap energy. This was the Meissner effect. These are the optical measurements. These are Alex's amplification for 2 dopings. You can see you get a temperature scale that depends on the doping. So all great. So, you can kind of, this was what I had in mind at the time. You have this phenomenal pump phonon amplify this guy. These are the oscillations, and you can think, this has also connections to polarity condensates, to time crystals. It's really very interesting sort of interface. Turns out, however, that if you look at this effect carefully, the theory was a little bit reductive in this following, because at the beginning, this is the work of Nilo Taherian, who's graduating now, and she's been looking at the following problem. She says, look, you got two phonons here, you don't have one. So in principle, you could have a parametric, you can either have this three-wave process, which is as good as any, but you can also have a four-wave process where basically you take two of these phonons, and the difference frequency between these two phonons generates pairs. So this is a four-wave, four-mode parametric process that in principle is just as good as this one. So once you start peeling your onion and you look at the process, there's just a lot of details. And this turns out to be actually very strongly connected to what Mohammed said, that this process doesn't really explain what we were seeing, precisely because the seed of this amplification process is an incoherent noise. And so I should not have an oscillation that always looks the same. A number of things should average out to zero when I do the experimental process. So, however, more importantly, if you either take the three-wave, one phonon, two plasmons, or four-wave, two phonons, and two pairs of the same low-frequency plasma at finite momentum, and you look at the calculated one-dimensional curves, they kind of look the same. So measuring this is actually an ambiguous process. So long story short, Nilofar spent a long time trying to develop these multidimensional methods. So this is some sort of NMR method where you pump the system twice, and you probe it, and then you create two-dimensional maps as a function of the inverse of this time distance and this time delay between this and this pulse. And so you create these maps, and now you have more information. This was done with Albert Liu, who's multidimensional expert, and he came to our group and sort of helped us think about this. So you can generate these maps. So this is not what Alex measured would be just the projection along one line. And now what's very nice is that you measure this map, and then you calculate the three and the four-wave maps, and it turns out that the three-wave process looks different than the four-wave process. So it turns out that this is not true, and this is really what we should be thinking of. And again, these are things that we're starting to think to now. So in principle, this is not so different. You should have parametric amplification of each one of these. You should have finite momentum. You should have a strain symmetry. You should have the same temperature. So everything that Alex saw is right, but it also applies to this. However, what's really strange about this is that this is not the generation of you shouldn't think about the amplification of a plasmon current, but you should think about the amplification of a squeezed state of these Judson plasmas that are connected to fluctuations of the superconducting phase. And so that's in principle different. And there's a number of detailed arguments that show you that if you're generating pairs of Judson plasmons, although these guys start individually from thermal noise, the covariant oscillations retain so what we're seeing in our time crystal response. Oh, right. And so Marius also showed that if you take this process, in reality, both processes, you can also explain the light-induced plasma effects. So this is where we are. We don't really know where we are. Why would this expel magnetic fields? What does that teach us about organics? I mean, there's like a million things that we don't understand. But in the cuprates, where we understand the modes, we've been looking at this problem for a long time, we're getting to something that is this kind of Floquet phonon-driven state that couples nonlinearly to squeezed. So you're basically pumping energy into the noise. You're not pumping the supercurrents. You're sort of periodically modulating the variance of the phase fluctuations of the superconductor in some way. And this maybe explains something. I don't know. We're not there yet. Right. So that's what I wanted to say. I mean, it seems that, and rather than amplifying the superconducting currents, which is what I tried to convince you of, we may be amplifying some sort of variance, and this is not what it is. And so I'm going to conclude by listing really these fantastic people that have done all this work. So where do I start? Sebastian and Giovanni did the Meissner effect. Michele is a sort of unbelievable experimentalist that does all of these things. Or Gregor also did a lot of enormous, very good stuff. He's now left us. Marius and Eugene for explaining us what it is that we're seeing. Nilo's graduating now. Also, she did the multidimensional. Alex graduated and is now with Nu. As I said, Michel first is a staff scientist. With us, again, nonlinear optics wizard. Albert now joined the staff at Brookhaven and is trying to set up these multidimensional methods. At Brookhaven, Michel Fechner is a theorist who tells us what modes do what. And this also sort of gives you a sense of just the amount of intellectual muscle that goes into these things that I'm excited to tell you. So thank you for your attention.
It was exactly 40 minutes. I guess suppose.
The speed of the propagation of the Meissner effect.
Yes.
Is the speed of the plasma that you use in the same expression of plasma
No.
you use in the last part?
No, it's a magneto. It's basically a photon-induced Meissner effect is basically an Austin switch, where you have a magnetic field, you change the susceptibility of material, you have a dB/dt at the surface, and this radiates a wave. It's an antenna, basically. So it's not